Sir,
Yes.
hello.
Yeah, tell me, I can hear you.
Yeah, can you please say that why the people are raising hand? I have some audio issue.
No, I can't hear you. Say it again. You said some action principle, and we also told you that we had these generators and the total time derivatives and stuff like that. Now, the action principle, you see, it not only provides us with these field equations, which is what we actually did. We also showed that if you choose our variables in a suitable way, we get constraint equations, okay, along with the field equations. So those were the field equations were the particle equations of motion of this individual particles. There was expression for energy. There was this Maxwell's equation. But this action principle also gave us what I call the generators, which everyone calls the generators, right? So showed it with G. Those are generators, okay? Now, the generators were something which was due to the total time derivative of whatever one thing, right? And generators basically provides the connection between conservation laws, whatever is conserved by the system. It can be local conservation laws also or global conservation laws, and invariance of the action. So if actions are invariant somewhere, then they will have generators and that will dictate your conservation laws, okay? Now, in classical mechanics, of course, you have seen this many times. You see that the angular momentum. So, for example, the last part, we knew that the time invariance and the time displacement of the Lagrangian of this action led to your energy conservation. Okay. Similarly, you know from classical mechanics that if you have rigid translation, then that gives rise to your momentum conservation. Or if there is a rotation, then that gives rise to your angular momentum conservation. Okay. So over here, this is stupid. It's still there. Again, it has gone back. If I don't write for like 2 minutes, even a minute, it just goes away. It's very frustrating. So let me start by giving, actually working out for you one of the conservation laws and related to the invariance and the generators in the system. Okay, we have done one. Let us do another one. So let us talk about rigid translation and see that just like in classical mechanics, it is also over here that things are conserved. Okay. So the first thing is, if you, as I said, if you look at the total action and its variation, then it gave you what was these generators. So if we have delta S, hold on. If you have this action minimization, delta S, let me get rid of my WhatsApp. So my delta S, which was this minimization of action, 0, that gave me my generators at the two endpoints, okay, from the total time derivative, remember? And this basically means that if G1 minus G2 is 0, then G1 is equal to G2. These were at two different times, which basically means that if I have G as a function of T, this has the same value at all times, or this is equal to 0. Okay. So this thing is conserved. So GT is conserved. So G is conserved. Okay. Now, this comes from and this is something that I don't know whether you have done it well. So in my classical mechanics, I spend quite a bit of time doing it, but I'm not sure that always people do it. So this comes from this principle, and you have of course heard this principle, but I don't know how well you have done this. It says if, so let me write it down. If the action S is invariant under an infinitesimal transformation, okay, then there is a corresponding conservation law, okay, and vice versa, actually. So it goes both ways. And this is the famous Noether's theorem. Okay. Just a minute, okay? I said I need 2 minutes break. So some work is being done. This guy is going out. Just give me 2 minutes break. Okay. This is a famous Noether's theorem. We'll start from it. Okay. Hopefully there will be no more disturbances anymore. No, don't worry. Okay. So that is called the Noether's theorem. Now, let us try to use this in in our electromagnetic action. Okay. So we are going to give the simple example of linear translation, and then one can do rotation and other stuff as well. So let us think of, let us draw this figure. Okay. So let's have some figure which will, so let me have some coordinate, which is the old one, some point over here, some point over here, okay, and this is R, this is old coordinate, and then this whole thing has a new coordinate, okay. The new coordinate, this whole thing is, let's say, displaced from the old coordinate by a small displacement, epsilon. And so the same point has a new coordinate, which is R plus delta epsilon. Okay, this is what it is. And we're going to use this to work out our conservation law. So what we have an infinitesimal displacement delta epsilon, okay, to a given point r in old coordinate. Okay, so new coordinate becomes r plus delta epsilon. Okay, this is what we have now. Now, if you look at the Lagrangian, okay, and if you look at the G that we had in the Lagrangian, so if we look over here, let's go back and try to find out here. This total derivative part over here, this one, okay. So if you look over there, then what we had was the G from the action minimization, the generator, which was given by this total time derivative. It's given by this part, which was the particle part. Okay, so pi dot delta Ri. Then there was a field part, which is 1/4 pi c dqr e dot delta a and minus h delta t. Now, for this infinitesimal transformation, so this is the particle part. Okay. For this infinitesimal transformation, the change to this particle part is just very easy to do, right? So the change due to delta E, change in the particle part. Okay. Particle term is basically just, so delta Ri becomes delta Ri plus delta E, and then you have to take delta Ri, subtract it out, so it's basically just delta E. So P dot delta E, delta, not delta E, epsilon. I'm saying delta E, it's basically delta epsilon. So this is basically delta epsilon, okay, dot summation of this is the change in the particle. The H delta T doesn't have any change due to a coordinate transformation because there is no coordinate coming in. However, there is a change in the second part of this G, okay, which is the one with the vector potential delta A. So there is a change in delta A due to this infinitesimal transformation delta epsilon that is there. Okay. So we have to find it what this change is and then put it back over here. Now, what we want is that if I have something at this point P, some field, okay, this value of this field, whatever the field is, it can be anything. So I'm making it arbitrary, some quantity, I'm calling the field. The value of this field, okay, is unchanged. So because field is a physical quantity, so the value of this physical quantity is unchanged. So if I see it from my coordinate, the old coordinate, it should still have whatever physical quantity. If I see it from a new coordinate, it still have the same physical quantity. That's the whole point of all these things. I mean, physical quantity remains unchanged. It should not change. There will be transformation. So the value of a field, let's say some field, let me call it some field, say F maybe tilde f at this point P, the value of this should be unchanged. Okay. So due to this rigid displacement, the value should still be unchanged. So functional form may change, but the physical value should be unchanged. What it basically means that if I have this P, okay, this thing, whatever I want. So this was a function of R in the old thing. This will be some different function, okay, of R plus delta epsilon. But the actual value should be same. So somehow this thing should behave. So now, if I look at this, then the change of the function at the same coordinate. So if you look at this, so these two coordinates are different. Okay. So when my coordinate changes, the functional form changes. So f becomes f bar tilde whatever. Okay. However, if I look at the same coordinate, so the change of the function f in the same coordinate, this I can show that my f basically, if I look in the same coordinate, this should of course be my thing plus some so some change in the function gives me whatever is in the old coordinate, same coordinates. The new function is this old function, but the coordinate now is the same. So now I can calculate delta f from here. I can calculate my delta f from here. So then I can calculate from here. Therefore, my delta f, the function of R, is basically, if I look at these two previous equations, I can write it as f R minus delta epsilon minus. Okay. And since these are at the same coordinate, I can expand it in spatial Taylor expansion. So then this will be minus delta epsilon dot divergence of so this is how some physical quantity will transform if I have a small rigid translation. Let us give an example, okay, of this. Think of charges. Okay, so as an example, take charges, and so if I have my charge density of R, okay, this is of course summed over all the charges with the delta function put in. This is what we did before. So this is I, Qi delta R minus R. Now, if every charge is displaced by a small displacement delta I, okay, then so if all the charges are displaced by delta epsilon. Okay. Then the charge density, we will have a new charge density now, and that then my new charge density rho r plus whatever my delta rho r. Okay. This will be now summed over qi. Remember, all the positions has been decreased by epsilon, so this will be delta, a function of r minus ri minus delta epsilon, because all the charges have been displaced. So this is a new charge density. Okay, so now I can write down where my delta r minus ri minus my delta epsilon, this small displacement. I can again write, because all of them are in the same coordinate, so I can do exactly like previously. So I can write it as delta r minus ri, okay, minus delta epsilon, sorry, not I, delta epsilon dot divergence of, so right here, tensor this is how I can do it. Okay. Now, what's next? So if I now compare this with my previous one, so I can find out what is my delta rho r is, right? So then, therefore, my delta rho r, okay, is minus of delta epsilon dot divergence of so now you see this is basically the same form as this. So the physical quantity behaves like this. Okay. So we can use this functional form to see what happens to your A. Okay. So then we use this functional form to what happens to your A. Okay. So write down the field part of the, so over here, write down the field part of this generator.
Sir?
Yes.
Whatever we have done only for the scalar
Please
part.
say loudly. I'm also hard of hearing slowly.
Whatever we have done only for the scalar part, right? These are the scalar fields.
Which one? In
The rho r act to the scalar field, right?
Yeah. And we didn't say anything about scalar or vector. It was some field.
Yeah, under translation, both will behave same. That is fine.
Yeah.
The rotation, everything changes, right?
Rotation will be different. So when you do rotation, yeah, rotation will be different. I will, rotation is a homework problem, but I will give you the first hint of the rotation, okay? How to do it. So rotation also, what you will see, if you look over here, this equation, the one that I'm, this equation, okay? In this equation, you will have to find something that will happen when the, so rotation, remember, you will have to have your delta R. Again, the rotation, so the way to think of it is in rotation also you will have a delta R, but the delta R will come in the standard way of having a rotation cross product with an R, right? So every rotation of some delta omega gives you an delta R. And once you realize that your delta R comes from a delta omega cross R, and this is the one line thing that I wanted to give, then you can write down an equivalent relation over here. And that equivalent relation, you'll see that has a different, so the vectors are changed in a different way. So your A's will change in a slightly particular way. So you have to, that will be a homework. So, but I will give you, as I said, I will mention you, I already mentioned something, and I'll tell you what to do. It will be easy. Just I'll give you the answer, but you should work out the detail. Okay, let's get back to this. So now I'm going to use this transformation rule to see what happens to A when I make this transformation, and the A basically is the generator of the field part. Okay, so I'm not going to work out all the details. So if I now look at the field part of G, this G is the generator, okay? Then this, remember, was minus dqr, there's a 1 by 4 pi c, then there's an E times delta A. Okay. So I'm going to use this over here. Use this over here, and I will write this as 1 by 4 pi c dqr pi delta epsilon dot grad. So this is exactly what I've done before. Same thing, you look at these equations again and again and you'll find that this is what it is. Once I have this form, then I have to use vector identities. Okay. So now use vector identity. Okay. The vector identity that has the curl connecting with these two dot things, dot products. So delta epsilon dot of A, right? This is equal to dot A minus delta epsilon dot grad. So use this vector identity. Once you use this vector identity, then you have written this part in terms of these two parts. Then you further use that B is curl of A, and okay, you use this two. And once you use these three things, a little bit of manipulation, you will find that this equation becomes like this. So this equation obviously will have now two parts, because you can see there are two parts over here. One part has given rise to two parts. So this equation will become, let me see this, hold on. It will become, right, so it will become 1 by C summation over I, then there is a QI delta. plus 1 by 4 pi c So you will find that this equation becomes like this. Okay. So I can write down my G, okay, the generator as, so I can take these terms together along with the particle term that was there before, and we can now collect the terms to get G in terms of my delta epsilon times some quantity P. Okay. Where this P, if you collect the terms, you will see that this P turns out to be, so there is a term coming from over here, the first part, and there's a term coming from the second part. The first part terms over here, there was a Pi from the particle side, so Pi and this will come together. So your P turns out to be summation over I, okay, Pi times Qi by Ca Ri, okay. This thing. Plus 1 by 4 pi c EQR E plus P. So I can rewrite this like this. So this is basically MIVI plus GQR. So what is this G? This is the, so in ED1, you must have seen this G, right?
Pointing vector.
No, this is the momentum density. This is the momentum density. Okay. Okay, so this is your, so now as you can see, dg dt, G means the generator G, is 0. The delta epsilon is an arbitrary, so your dp dt must be 0. So your P is conserved, right? Since the action, okay, is invariant under arbitrary delta epsilon, okay, so I'll have 0. This is my action is invariant, so G1 minus G2 is its variance, and so basically my P1 minus P2 dot delta R. So delta epsilon is basically delta R, right? That is the small thing. And therefore, my P1 is equal to P2. So the total momentum, very important, momentum, P conserved. So the kinetic momentum plus the field momentum, this total momentum is conserved. Okay. So this total momentum is conserved. So if I take the total action and make a rigid translation, delta R a linear translation for which the action is invariant, then it tells you that your total momentum is invariant. Today, I will not have a chance to do because I don't want to, because that will take a bit long time, so I will not have enough time to finish it. We are going to, next day, we are going to actually talk a bit about what happens. So see, in this thing, whenever we're talking about conservation laws till now, it was the total energy it was conserved, right? The homework that was given. Over here, the total momentum is conserved. But we can also talk about things which are very local. So we can also talk about local conservations, infinitesimal small conservation laws in local areas instead of global conservation laws. And that is actually quite important. And we'll see in the next class how that invariances and conservation laws comes about. Now, given this, the way you have done this, your homework, okay, is to do this. So your homework is, so what is your homework? You start, so show explicitly, oops. So show by explicit calculation, okay, that momentum is conserved. So over here, we have shown that the momentum is conserved by using generators and showing that the action is invariant under small displacement, infinitesimal displacement. But what I want you to do is I want you to show by explicitly calculating. So you take this, so what you want to show, so that is show this, okay, show ddt of dqr g, okay, this is equal to 0. Show by explicit calculation that this is 0. And if you guys are more adventurous, then there is homework 2 where show that total angular momentum is conserved if the action is invariant under a rigid rotation. Okay. Rotation in the coordinate vector. That is delta r is equal to delta omega plus r. So if you have everything rotated by the same amount, then you have to show that the action is invariant, and then you show the angular momentum is conserved. So over here, what you will find, so first show that my A, remember the A in the new, just like the old coordinate and the rotated coordinate, the A in the new coordinate, okay, r plus delta r, that will be A in the old coordinate plus Oops. Okay, so this is what you need to show. Now let us go a little further and talk about conservation laws, which, so this kind of conservation laws is there in mechanical systems, right? So you have no energy, angular momentum. These are there in mechanical systems also. On the other hand, we are talking in electromagnetism. So our system, other than this mechanical conservations, also has something extra which this mechanical dynamical systems did not have. Okay. So let us talk about something new and talk about what goes by the name of gauge invariance. So this is also related to conservation laws. Now, in the standard conservation laws, we have in the dynamical systems, we have energy. So standard conservation laws in dynamical systems, energy, momentum, angular momentum, whatever. Okay. However, in the electromagnetic system, there is one additional conservation law, because electromagnetic system means we have charges. So in EM system, there's an additional conservation. Okay. That is the electric charge. Okay. So electric charge is an extra thing that needs to be conserved in a ED, electrodynamics, other than what is already there. This does not come in ordinary classical mechanics. Everything else, what was there in classical mechanics, you can write down a counterpart over here. But this part does not appear in ordinary classical mechanics. So this actually is connected to the invariance of the electromagnetic field related to the potential. So because the electric and magnetic fields, these are connected to the potential in a particular way.
Sir, can you please repeat that point? I lost my connection.
Which one? Okay.
That.
So what I was saying, so did you miss everything that I said over here?
Yeah, from the gauge invariance.
From the gauge invariance, yeah. So yeah, so the gauge invariance. So in standard dynamical systems, we have the standard conservation laws, which is the energy, momentum, angular momentum. You can write down a few more, okay? And these you can also do for the electromagnetic systems, which you have done already. Okay. Now, there is one thing extra which is there in ED, which is not there in mechanical system, is that we have charge. So there is one more conservation, that is the conservation of the electric charge. Okay. And this conservation of electric charge can again be connected to some invariance of the Lagrangian to something. And it turns out this is connected to the invariance of the electromagnetic field related to the potential. So this conservation is related to the invariance of the electric fields, okay, which are related to the potentials. Now this gauge invariance, why gauge invariance? This has a history. It has nothing to do because the word has stuck due to the historical way this subject has developed. I mean, if it was done later, maybe we would have not called it any gauge invariance. Okay. So, but it's just a word nomenclature that is due to more of a history of it instead of really, really connected to any gauge over here. I mean, there's no gauge choice over here. So later we will see, we'll not do it, but when you do other advanced stuff, there is something called gauge choices, in which we equations become easier to solve. Okay, and ultimately we can go back and get the same physical quantity. Gauge invariance, gauge choices are different. That has a much more physical meaning. Okay, this is more of a historical context. So remember, if I have my ACE, if I have my vector potential, if a vector potential goes to A plus some gradient of lambda, okay, so lambda is something arbitrary, okay, some arbitrary function, and at the same time my scalar potential goes to phi minus 1 by c del lambda del t. If these two things happen at the same time, okay, then my fields, where E is given by minus 1 by c del A del t minus grad phi, and B is all of A, these remain unchanged. So if E and B, they remain unchanged, then the Lagrangian remains unchanged, right? So for this kind of thing, the Lagrangian will remain unchanged. At least the field part of it remains unchanged. We are interested to what happens to the particle part of the Lagrangian. So let me write down the Lagrangian again, okay? The field and the particle part. The field part is trivially unchanged because your E and B are unchanged. So the field part is trivially unchanged. Although the field part has other things other than E and B, there's also an A part and phi in it, but the field part is trivially unchanged, you can see. So let me write down the Lagrangian, full Lagrangian that we did, okay? So recall there was this particle part, so I have my air, which was summed over I, Vi, so Vi dot T minus Vi, then plus half Mi Vi squared, then there was minus Vi phi plus Qi by C, Vi dot A. And then there was the field part, which was 1 by 4 pi R by C del T minus grad phi minus B dot curl of A plus half B squared minus B squared. This was the full Lagrangian. Now over here, this part one can show trivially that if I do that transformation, this gauge transformation that we call, if I change my a and phi, then that part Lagrangian remains unchanged. Question is, what happens to the particle part? Now, when we want to go to the particle part, we have to be a little bit careful. Okay. The fact is, in the particle part, of course, remember, we will change a to a plus grad of lambda. Okay, that a is there in the particle part. Okay, and phi is also there in the particle part. But that is not all. You have to be careful. Is that if I want to change something, you have to be careful that if those quantities are implicit inside some other quantity, then we have to be careful about that. So the quantity that you have to be careful about is the velocity. So remember, to do the particle part, to do the particle part, the important thing to do is remember that the velocity v is a physical quantity. Okay. So it must be invariant. If I do some gauge transformation to a and phi, the velocity should not change. It's a physical quantity. It's what things are moving about. That should be invariant. Okay. So v should be invariant. Okay. Which basically means, what does it mean? It means that my E minus Q by CA, this thing must be invariant under gauge transformation. So this must be invariant under gauge transformation. Okay. So now I have to somehow, because I know how A is changing, so I have to somehow change the P such that this whole quantity is invariant. So this basically means because, so this implies, because I know how A is changing, so my P must under gauge transformation do as P plus Q by C . Okay. So now rest is easy. So now you can go back and put all these things into your equation. Okay. So I put this P in the equation over here. I will put my A's, I will put whatever, everything, phi's in the equation. So when I do that, so I put all the invariances, put all the invariances in L. You will see that my L will of course go to some new L prime. And I'm not going to do the algebra, it's just 2 line of algebra. You'll see that the new Lagrangian, okay, is related to the old Lagrangian L plus an additional term which will be due to this lambdas, this terms containing lambdas. Okay, so this will have a summation over I. Okay, Qi by C lambda dot Ti T minus y in the first term. Then we will have a Qi by C del lambda del T, and then we'll have again a Qi by C y dot Now what? So now I can collect all these terms together, and I can write this down as L plus summation over I Qy by C lambda del T plus check that you can do this. Some of the sums will cancel out. So now I can go one step forward and write this as L. So my L prime, this one becomes L. I can combine these two terms in the bracket, okay, as one term, ddt of I Qy by C lambda right. So this is what we can do. So take the time derivative, take the special derivative, and then combine it into a total time derivative. So what do we have now? We have a total time derivative. Okay, so we have the Lagrangian. So this new Lagrangian is this old plus a total time derivative, okay, added. So the transform Lagrangian under this gauge transformation is the old Lagrangian plus an additional total time derivative, okay, which basically means there will be a total time derivative which will go in the action, okay. So the total time derivative, remember, does not change your equation of motion. So remember, when we did the equation of motion, we said the total time derivative does not change the equation of motion. So total time derivative doesn't change equation of. And so the change of the action is only due to, when you have total time, only due to the endpoints. So if I have my action, so change, so this thing, change in action is only at endpoints. So I can write down my new action, changed action, which will be S plus some endpoint variation. So let me write the small s, S2 minus S1. Okay. This change is due to the endpoints when it comes to a total time derivative. So your generator, okay, this is G plus delta. Now, what I want to do is go a little more to understand what this means. So we have first found this important relation that due to gauge transformation, the Lagrangian is changed by an addition of a total time derivative. And we recall that if we have a total time derivative, then that does not change the equation of motions. Okay? And you have these generators which appears, which were at the end, which are basically the endpoint contributions. So now we'll go and write down, okay, this previous equation L by substituting. So write down to see what this means. Write L prime substituting. So write this L prime which has this first one right over here. substituting in bi is equal to dri dt. Like this. So then this one will change. Okay, so we write it down like this. This one will change, and what we'll have is my L prime minus L. So just take the old Lagrangian on the left hand side. Will be, if you do it, just so first part will drop out. Certain small things will drop out. You just calculate it. It will be 1 by C hold on. This is what we'll get when I substitute this in the original Lagrangian. Okay, this is what we are going to get. Now over here, the lambda, remember, was an arbitrary function or arbitrary change. If I want to go into conservation laws, remember Noether's theorem, the change has to be infinitesimal, right? So what we want to see is that what happens when this change lambda is infinitesimal. So we need to see what happens when the change lambda actually is infinitesimal. Let's say delta lambda. Okay. So lambda going to delta lambda, what will happen? Okay, this change lambda is infinite, because remember, as I said before, when we started in the Noether's theorem or beginning, we basically said that if there's an infinitesimal change and that infinitesimal change does not change the action, then that is related to a conservation law. So if I do this, then you will see that my delta S, remember I had a delta S defined over here, a delta S defined over here. Okay, so my delta S over here, then I have a delta S. Okay, this will be G delta lambda 2 minus G delta lambda 1, this total derivative term, minus, so this is thing you have to work it out a bit, dt dr 1 by c delta lambda del t plus this is what your delta S will turn out to be. Now, if we go back to this equation, initial equation, okay. So let's go back to this equation here. This equation. Look at this equation. The second term was the one which give you your delta S, right? The first term give you your S, the second term give you your delta S. Okay. So if I go back now over here, this basically means, okay, I have my, so, okay, let me try to connect it again. So how do I connect it? Show it together. So look at this equation over here, which I've underlined with this thing. So that was the DL part, the delta L part, that will give you a delta S. Okay. And this basically tells you, okay, that my delta S, my, oh, my delta S, okay, gives me that my delta S. So these notations are becoming too convoluted. I want to write down my G due to the small change of delta lambda. Okay. So both the endpoints have a small delta lambda change. Changes in endpoints are due to delta lambda, and that affects both the endpoints. That's why I'm saying G delta lambda. This will be basically G to R and by C delta lambda. This is what it was. Again, look at this equation, green underline equation, and this equation over here. Okay. Now look at this equation. Now look at this equation. Okay. Look at this equation. So from this equation, since only endpoint variations, okay, can give to change in action, okay. Our stationarity, this is delta S equal to 0, stationarity of the action demands, okay, my dqr delta lambda by C. So this comes from this part, okay. The second part of this delta S, this comes from there by C, okay. Then del over del T plus divergence of J. So, okay. So there are two parts. One part, this G part over here, okay. The G part is the total time derivative given G, that is conserved. So that gives you a 0. That does not contribute to your thing. And then there is a second part. And if I want the stationarity of the action to be there, then this second part should also be equal to 0. And if the second part is equal to 0, then this part over here is equal to 0. Okay. And since my delta is arbitrary, since my delta RT, this is arbitrary. Okay. This tells me that if this part is equal to 0, then this implies that my del rho del t plus divergence of J, that must be equal to 0. So what does it mean? It means that if we have an infinitesimal if we have an infinitesimal gauge transformation lambda, then stationarity of the action implies that this must be equal to 0. The del rho del t plus divergence of J must be equal to 0. And this is nothing but local charge conservation. So due to gauge invariance, due to infinitesimal gauge invariance, what we have is we have a local charge conservation. Okay. So if the delta lambda is a function of R and T, okay, if it was a small gauge invariance at every position R and T, locally the charge is conserved. So charge conservation means locally there has to be a local gauge invariance, or inversely a local gauge invariance. Because remember, I have written delta lambda as R and T, means there is a local conservation of charge. One can, so I have like one can go one step further, okay, is that, okay, what about local conservation of charge? What about all the charges? I mean, that also has to be conserved, right? Because we do not create any charges, destroy any charges in it. So total charge must also be conserved. So this will come if instead of delta lambda being R and T, let's have my delta lambda is equal to some constant value. Okay. If I have my delta lambda constant, then remember del t is all these things, or the gradients are all vanish. Okay. So this basically tells me that my delta A is equal to 0, because delta A gave a gradient of lambda. So the delta lambda is constant and the gradient is 0. So, and also delta phi, this is equal to 0. Okay, so there is no time and no spatial dependence. Delta lambda is constant. Then what I have is that you go back to this equation over here, this equation over here. Okay. So in this equation, so second equation is automatically becomes 0. The first equation that we have, then the G for a delta lambda is equal to constant. This becomes, the delta lambda is constant, so I can take my delta lambda outside my integral because delta lambda is constant. So then it becomes delta lambda by C, and then dqr times 0. But what is the volume density integral of the charge density? It is the total charge. So this basically means Q is total charge is conserved, because G gives you the conserved quantity, right?
Sir,
Yes.
when we are doing the space integral, this volume integral, are we taking it over the full the space or some specified space only?
Again, say it slowly, because when you're, I don't know how the voice quality for me over here is, but when you voice quality over here is very bad, so things get very so slowly, please.
So when we are doing this space integral, meaning the
Yes.
volume integral,
Yes.
are we doing it over the whole space?
Whole
Or
space,
doing
yes.
it-
It has to be our whole space.
Okay.
So remember, always it has to be our whole space. Even when we did, when we talked about local charges, go back when we talked about local charges, and we had this rho as with this delta functions. we remember over there, we mentioned, go back to your notes, we mentioned that the volume taken is always such that it is covers all the charges. So it's always whole space. Sufficiently larger than the region where the charges are. That's the most correct statement. So it is always whole space. Or volume
So
which is
it's like there will be no charge near the boundaries. Mostly will
no,
be
there is no
outside
charge near the
boundary.
boundary. Yeah. I mean, as I said, the right way of saying is that the integral is over a volume which is sufficiently larger than the volume containing the charge. So you think of two volumes, V1 and V2. If V1 contains the charges, then you must have a V2 which is larger than V1. And typically we make this V2 very large so that, you know, surface terms can drop out and stuff like that. So this is how we did when we did actions. All these things came into play. Go back to your my I have mentioned it. I remember I have mentioned it. So go back to the lectures and over there. So from gauge invariance as a function of R and T, we got local charge conservation. From a constant gauge invariance, if it's not a function of R and T, we get a global charge conservation. Okay. Next day, what we're going to do is we're going to go a little more, as I said, okay, and basically we'll talk about gauge invariance and local conservation. So we have till now, other than the local charge conservation, we have talked about conservation laws previously, where remember we had this R or whatever. Those are global conservation laws. We are going to talk a little more about these gauge invariances and talk about local conservation laws. So if there is something which is globally conserved, maybe at small spaces, at small pockets, there are some other conservation laws. You can basically get a little more out of this, out of the fields. So that's what we're going to do next day. It will take at least 30-40 minutes, so I will not start today. Okay, and once that is done, then you know, hopefully the first part of Maxwell's equation and invariance, conservation laws, these things are done, and then we can move on to the next part, which is covariant form and special theory. Although I have to be honest, I will not do special theory in great detail. So I will do it just as much as you need to know or is needed to do my ED stuff. Okay. And what else? I actually had one question and I've forgotten this question now. Yeah, I don't remember it. So Friday it is 4:15, not 4 o'clock, because there's a colloquium till 4 o'clock. Okay. So all Fridays. So just to be all Wednesdays it is 11:30, and Fridays is 4:15, because there is a cosmology colloquium from 2:30 to 4. So otherwise there's too much of hassle in between. So we'll start at 4:15, and Wednesdays will start at 11:30. Okay. I don't think there is anything else I want to say now. So we'll basically stop then. And I will ask Avitro and Anuma to slightly redo the things, and we'll send you the question papers along with these two problems also. Okay. Good.